In this lesson, we'll introduce the economic theory of choice under certainty. Individuals behave according to their risk preferences, which determines their reality of wealth. In this backdrop, we'll discuss the indifference curves for investors and how these concepts help us in arriving at the risk-return framework in financial markets. We'll also discuss the expected returns and actual returns in financial markets. We'll examine various measures of risk in financial markets and their computation. Economic theory of choice under certainty. In this video, we'll discuss about economic theory of choice under certainty. We'll examine how individuals can optimize their time pattern of consumption with the help of financial markets. Consider the example of an investor who will receive 10,000 rupees at the end of years 1 and 2. Also, assume that the only financial instrument available can be borrowed or lent out at an interest rate of 5%. The question we are trying to explore here is as follows. What should be the consumption and investment pattern of this investor? To answer this question, we need to first define his opportunity set. At one extreme of the options available is to consume rupees 10,000 in each period and save nothing. This option is shown as point B in the figure here. If he saves all the income, that is invests at 5% in period 1 and consumes everything in period 2, then the amount he invests in period 1 will become rupees 10,500 including interest in period 2. Adding this to the second period income, the total amount he can consume becomes rupees 20,500 as shown here in point A. Another extreme is to borrow an amount against the income in period 2. This will be 10,000 divided by 1.05 equal to rupees 9,524. So he can consume 19,524 in period 1 itself. This is shown by point C. And so, as we can see here in the diagram, it appears that all the choices available to the investor or the individual can be represented on the straight line AC as shown here in the figure. It is easy to understand that the consumption of the individual is constrained by his income. If the consumption in period 2 is C2 and in period 1 is C1, we can write a simple equation that defines the relationship between income I1 and I2 and consumption C1 and C2 as shown here. This will be as follows. C2 equal to I2 plus I1 into 1.05 minus C1 into 1.05. Here I1 equal to I2 equal to 10,000. So if the consumption period 2 is C2 and in period 1 is C1, we can write a very simple equation as shown here that defines the relationship between income I1 and I2 and consumption C1 C2. For example, 10,000 minus C1 into 1.05 is the amount available in period 2, which is equal to amount saved at 5% interest rate after consuming C1 from the income of 10,000. So the resulting equations are C2 equal to 10,000 plus bracket 10,000 minus C1 into 1.05, which can be further simplified to write C2 equal to 20,500 minus 1.05 C1. The consumption pattern or opportunity set of the investor or individual shown here is defined by a simple straight line as was given in equation 1 or equation 2. This is an equation of straight line AC as we saw in the figure that passes through point B. The slope of this line was minus 1.05. The slope reflected that for each additional unit the investor consumes in period 1, 1.05 unit is consumed, that is less in period 2. This means he could have saved this amount 1 unit to earn 0.05 unit interest and consume 1.05 units in period 2. This line AC that we saw, it represents the set of choices and it is also referred to as the opportunity set. The question still remains here is there any particular point on this opportunity set that is most optimum to an individual? We'll have more to say about this in the next video. To summarize, in this video we defined the opportunity set of individuals. An individual who is more of consumer would like to borrow and consume as much as possible. Another individual who is a saver would consume less and would prefer to invest more. These two cases represents two extremes of the opportunity set and all the individuals would lie in between. The straight line joining these two extreme cases will represent the opportunity set of different individuals. Indifference curves and interest rates. In this video, we'll discuss the indifference curves and we'll try to understand how individuals maximize their utility on the opportunity set. Indifference curve or utility curves as they are called represent those points on the consumption region where the consumer derives the same utility by moving on the curve. That is, he is equally happy on any of the points on the curve. For example, in the figure shown here, we plot utility curves along the consumption axis. For an investor, four utility curves are drawn, that is I1, I2, I3 and I4. The investor on the curve I1 is equally happy or has the same utility whether he is consuming at points A, B or C. However, if he moves to I2, his utility is reduced. If he moves to I3, his utility is further reduced. The ordering, that is I1 greater than I2 greater than I3 is greater than I4, assumes that more is preferred to less. Also, please remember, if we are consuming more and more in a period, then the marginal utility of the consumption in that period as compared to the other period comes down. For example, consider a situation where we are heavily consuming in period 1. If we increase or decrease the consumption by delta 1, then the corresponding change in period 2 to maintain the same utility is much lower. Similarly, if we are consuming much less in period 1, then any increase or decrease in consumption by delta 1 dash in period 1 would require a much higher or lower decrease or increase in period 2. A common ground or solution to this problem is determined by the opportunity set and utility curves. This is shown in the figure here. On the opportunity set, we aspire to achieve maximum utility. This is obtained at point D, which is at the point of tangency between the opportunity set and indifference curves. Any other indifference curve will be above the opportunity set. One interesting observation is to be made here. If the optimum consumption is closer to point A, that is higher consumption in period 2, then the investor is effectively a lender at 5%. Similarly, if the optimum consumption point is closer to point C, then the investor is effectively a borrower at 5%. Somewhere in between, say point B, the investor is neither a borrower nor a lender at 5%. Now, summing across all the investors who wish to lend provides 1 point on the supply curve. Similarly, summing across all the investors who wish to borrow provides 1 point on the demand curve. As interest rates vary, full demand and supply curves are generated. Thus, the equilibrium interest rate is obtained when the amount supplied is equal to the amount demanded, called as the market clearing condition. Therefore, two key factors, that is investors' income and taste and preferences, lead to the determination of interest rates in the market. The above case pertains to a single financial instrument. What if there were two financial instruments? The first instrument has 5% interest rate for lending and borrowing, and the second instrument has 10% interest rate. Now, investor would prefer to lend at 10% and borrow at 5%, and therefore the optimum region here would be A dash BC dash as shown in the figure here. However, this seems to be not feasible. Common sense would suggest that this situation is unstable and nobody would like to invest at 5% and borrow at 10%. However, we do observe financial instruments with different interest rates. Now, this has to do something with the risk associated with the different interest rate instruments. To summarize, in this video, we examined the indifference curves for individuals and their role in utility maximization for individuals with respect to their opportunity set. These maximum utility points determine whether an individual is a borrower or investor. When aggregated across all the individuals, these maximum utility points provide demand-supply curve for a market. And this demand and supply in funds help us in generating market clearing interest rates. However, this analysis suggests a single clearing interest rate, while in real markets, we do observe financial instruments with multiple interest rates, indicating the presence of uncertainty or risk in market conditions. In this video, we'll introduce the concept of expected returns and see how it is different from actual returns. Consider an SBI fixed deposit and investment into mutual funds. How much return we should expect from these investments? From SBI fixed deposit, probably a fixed return of say 7%. What about investment into mutual funds? Maybe 10% or even higher. Why should we expect different returns from these instruments? Because these instruments offer different degrees of risk to the owners of the instruments. For example, SBI fixed deposit is safe, and for a very high degree of surety, you know that your principal and interest amounts will be paid back at the time instrument matures, that is, the holding period. However, in case of mutual funds, there is no such surety, and you may even get an amount that is lesser than what you invested. This uncertainty of outcome is called risk. Let's come to the computation of returns. Generally speaking, return from an instrument has two major components. First is capital appreciation or capital gains, which is ending price minus opening price. And then interest income or cash inflow from holding that instrument, that is dividends or interest from fixed deposit. Consider a simple example where price P naught, that is the price at which you bought the instrument, is 10 rupees. And the instrument is held for 1 year. The price at the end of the year is P1, which is 15 rupees. Also, during the year, the stock gave you a dividend of 5 rupees. Then, please note the following computations. Capital gains in the form of change in the price of security, which is 15 minus 10 upon 10, which is 50%. And cash inflow in the form of dividend or interest income, which is 5 upon 10, is 50%. Assuming there are no taxes, the overall return that you have is 50% plus 50%, which is 100%. This can be easily computed as follows. Total return on the instrument or holding period return is equal to cash inflow plus capital appreciation divided by initial investment. Here, the initial investment is the value of the investment at the beginning of the period. In this case, 5 plus 15 minus 10 upon 10, which is equal to 1 or 100%. Consider the following statement. Stock A offers 10% return and stock B offers 20% return. Which one is the better investment? Is there some piece of information missing? Of course, we need a holding period. For example, if stock A offers 10% in a week and B offers 20% in 2 years, surely they are not comparable. Still, we are not saying that A is better than B. We'll come to that later once we introduce the risk. Now we'll come to the computation of actual returns and a comparison between arithmetic averages and compounded returns. Consider investment in stock that is held for 3 years with the following closing prices. Assume that no interest or dividend is offered. So we can see the timelines. At t equal to t naught, price is p naught, which is 100. At 1 year end, price p1 equal to 110. At 2 year end, price p2 equal to 121. At 3 year end, p3 equal to 96.8. Let us see what the returns are for different holding periods, that is T0 to T1, T1 to T2, T2 to T3. So RT0 to T1 equal to 110 minus 100 upon 100, which is equal to 10%. And RT1 to T2 is 121 minus 110 upon 110, which is 10%. And then RT2 minus T3 equal to 96.8 minus 121 upon 121, which is equal to minus 20%. Now you are expected to compute average returns from the investment. Your accountant tells you that average return from the investment is equal to 10% plus 10% minus 20% upon 3, which is 0%. Is he correct? Please note, although we'll discuss it later, this is called expected return, but we'll explore this concept in more detail shortly. The intuition that he is wrong comes from the fact that you are left with 96.8 at the end of the holding period, which is 3.2 rupees less than your original investment. Surely your investment yielded you a negative return, but how much negative, that we'll see. This suggests that in this context, arithmetic averages are not exactly correct, and so we'll focus on the compounded returns or geometric averages. From our definition of holding period returns, total return or holding period return in this case amounts to, with no dividend or interest income, as 96.8 minus 100 upon 100, which is minus 3.2%. This return, however, is for 3 years. What about annual returns? Should we divide it by 3? Similar to the simple arithmetic averaging scheme to get the annual returns? But haven't we seen that arithmetic averages are not correct in this context? So we move to our friend, that is compounded returns. As per the compounding scheme, consider an average annual return of R bar on this investment. Then the total return or holding period return for 3 years should be 1 plus R bar raised to the power 3 minus 1, which is equal to minus 3.2%. Solving this equation, we can easily find that R bar works out to minus 1.07825%. We can back calculate this number to check if we are correct. That is 1 plus minus 1.07825 upon 100 whole to the power 3 minus 1 should be equal to 0.968. Also, the negative return of minus 1.078% seems fair, unlike the 0% return that we obtained from the simple averaging scheme. Please note that the above discussion holds in the context of or the calculation of actual returns. The actual returns are different from expected returns, and we'll come to the expected returns in a short while. For that, we need to understand the expectation operator. Consider the table shown here in this slide and a simple game like this. If you invest rupees 100, there is a 10% probability that you will end up with 140, which is 40% return. 20% probability of ending up with rupees 120, that is 20% return. 30% probability of 100, that is 0% return. 20% probability of 80, that is minus 20% return, and 20% probability of 70, that is minus 30% return, as we can see here from the table. Now, a very simple way to compute expected returns with the formula shown here is expected returns RIT is equal to sigma PT into RT, where T moves from 1 to T. We'll explore this formula in more detail now. What is our expected outcome from this game? From our understanding of simple probability computations, we know that the expected value of this game can be shown as follows. Expected return from the game equal to 0.1 into 40% plus 0.2 into 20% plus 0.3 into 0% plus 0.2 into minus 20% plus 0.2 into minus 30%, which is equal to minus 2%. We are simply multiplying returns with probabilities. Please note that we'll get the same result even if you work with absolute value of outcomes, that is rupees such as 98 or 100. However, in financial markets, it is preferred to use returns instead of prices. A more general way to represent the expected returns would be something similar to expected return expectation of RIT equal to sigma PT into RT, where T equal to 1 to T. Here, RITs are the returns on security RI for period T with the probability of PT. In this case, we have T discrete outcome of returns for which we are given the probabilities. What if we do not have these probabilities and we only have past returns and all the returns are equally likely? Consider a special case if all the scenarios have the same probabilities, that is P1 equal to P2 and so on up till PT. And since we know that summation of all the PTs are equal to 1, that is sigma PT equal to 1, T equal to 1 to T, and therefore P1 equal to P2 equal to P3 and so on equal to PT, which is equal to 1 by T. Therefore, our formula of expected return becomes expected value of RT equal to RT bar equal to 1 upon T sigma RT T equal to 1 to T. This we saw earlier as well. This suggests that averaging of observed returns to obtain expected average return is a special case where all the return outcomes are assigned equal probabilities. To summarize, in this video, we introduced the risk return framework in financial markets. We examined the computation of actual returns and expected returns and discussed the contrasting differences in these. Lastly, we also discussed that averaging of returns is a special case of expected returns wherein we can assign equal probabilities to all the possible historical return outcomes. Let's have a look at one simple example and try to compute this. The numbers are exactly similar here, and only difference is that now the probabilities are not given and we are assuming that all the probabilities are equal. So therefore, we'll add up all the 5 observations of return and divide them by 5. The key question that remains and that we would discuss in next video is what are these expectations are based upon, which is risk. Please examine the return distributions for three investment opportunities: investment 1, investment 2 and investment 3. If these three opportunities are given to you, which one would you choose between investment 1, 2 and 3? Let us examine and compare investment 1 and 2. If you notice, the mean or expected return for both the investments, that is investment 1 and 2, are same. However, the prospects of investment 1 are more scattered and more deviated from its mean, as shown or as is visible in the more scattered nature of returns around the mean. This is also reflected in the fact that the standard deviation of investment 1 is much higher at 20% as compared to investment 2 at 10%. We'll wait to see the computation of this standard deviation for now. The standard deviation is a measure of risk. The variance and standard deviation of returns are two important measures of risk or spread around the mean or mean deviation. They represent the risk associated with the stock. We'll see the formula shortly. However, given that their mean or expected return is same, but the standard deviation of investment 2 is less, you would prefer 2 over 1. Now let us compare investment 2 and 3. For both of these instruments or securities, standard deviation is same at 10%. However, the mean of investment 2 is lower while the mean of investment 3 is higher at 20%. And therefore, you would prefer, as a rational investor, you would prefer investment 3 over investment 2. So while comparing 1, 2 and 3, we notice that an investor would prefer higher expected return or mean return for a given amount of risk or standard deviation, and for a given amount of expected return, they prefer lower risk or lower standard deviation. Now, let us move to the computation of variance and standard deviation. It is quite similar to computation of expected returns. Please remember that uncertain outcomes in financial market lead to risk. For example, if the outcome is certain, as we discussed about SBI fixed deposits, then there is no risk, and that kind of instruments are called risk-free assets. The second important thing to remember here that a person can be risk averse, risk taking or risk neutral. Generally, in financial markets, a more practical case is that investors are risk averse, and these investors are therefore called rational investors. For these investors, risk is a very important property, and this risk is measured through variance or standard deviation, which is very similar to the computation of return. This is given with the formula here, where expectations of variance is equal to sigma pi into RIT minus RI bar raised to the power 2, and this is your variance. The square root of this number will give you standard deviation. Now, in this formula of variance, where we are multiplying probabilities with squares of returns deviated from mean, we'll again make similar assumptions as we made in case of returns. That is, if all the observations are equally likely, if all the past observations are equally likely, that is P1 equal to P2 and so on. And we also know that summation Pi equal to 1 because summation of all the probabilities has to be 1, and therefore P1 equal to P2 and so on up till Pt equal to 1 upon T. We can simplify the variance formula as shown here, which is 1 upon T summation RIT minus RI bar raised to the power 2. Often while working with the samples, instead of using 1 upon T, we tend to use 1 upon T minus 1. However, detailed exposition of this formula is not needed here. The idea here with this formula is that when the variance is computed for sample of observed returns, a more efficient and unbiased measure is provided when 1 upon T minus 1 is used. The only change here is that instead of T, we are dividing by T minus 1. This accounts for the loss of 1 degree of freedom because we are working with samples. We also note here that the use of subscript I in representing RIT and standard deviation sigma I of returns for security I. When we'll work with portfolios, we'll use the subscript as P. For example, for market portfolio, the subscript will be M. At this stage, it is important to have few words about normal distribution. Security returns are often found to be very closely aligned to the properties of normal distribution. For example, here we have plotted S&P 500 returns and superimposed normal distribution along with the S&P 500 returns. It appears that the frequency distribution and probability distribution plot of security returns looks very similar to normal distribution. And that allows us to employ normal distribution in various applications related to forecasting and prediction and risk management of financial instruments. The reason is that normal distribution can be very easily defined by two parameters, which is mean and variance. Mean or expected return for any security can be easily computed using the formula shown here, which is PI into RIT, or the average of historical returns as we have seen earlier. And similarly, variance can also be computed as PI into RIT minus RI bar raised to the power 2, and the square root of this number is the standard deviation. Now, once we have this mean and variance, we can easily define a normal distribution, convert it into standard normal distribution as well. And then once we have the normal distribution, we can make all the predictions about security returns. For example, we can easily predict with how much confidence, let's say 95%, we are expecting returns to lie in a certain interval. So all the concepts that probably you would have heard about interval estimation, hypothesis testing, statistical inference, we can perform by assuming that security returns follow normal distribution, which is a reasonable approximation. And given the fact that normal distribution can be easily defined with its mean and variance, it becomes much more convenient to employ normal distribution in modeling security price returns. We'll see some of these applications as a part of these courses. This includes wealth management and portfolio investing course and algorithmic portfolio management course as well. Now let's look at the computation of the variance. Let's go back to our example game where we had certain probabilities associated with certain return observations. Now using this formula of variance, that is PI into RIT minus RI bar raised to the power 2, let's try and compute the variance and standard deviation of this event. We have already computed the mean RI bar as minus 2% for this. So we have the mean RI bar as minus 2%, we have the probabilities, and we have the expected returns. So let's look at the computation. First, we'll compute mean deviations, that is RI minus RI bar, which is, for example, 40% minus 2%, which is 42%, and so on up till minus 30% minus 2%, which is 28%. So we have mean deviations. Now we need to square them. Each of these mean deviations will be squared, that is Ri minus Ri bar raised to the power 2 will be computed. Then we'll multiply them with corresponding probabilities. For example, 0.1764 into 0.1, which gives us 0.01764, which is nothing but Pi into Ri minus Ri bar raised to the power 2. So on and so forth. We'll move up till 0.0784 into 0.2, which is 0.01568. Now we have probability into square deviations, that is Pi into Ri minus Ri bar raised to the power 2. If we sum up all of them, as we can see in the slide, we get the variance as 0.0496, and the square root of this variance is standard deviation, which is 22.7%. With this, we conclude the computation of variance and standard deviation as a risk measure. To summarize, in this video, we discussed how to compute risk in financial markets. Risk in financial market represents the scattered nature of returns around the mean or expected returns. More spreaded or scattered observations indicate a higher variance and therefore a high amount of risk associated with that security. In this video, we'll discuss the effect of compounding on interest rates. Interest rates can be sometimes misleading. One should carefully examine the frequency of the interest payment and compounding period of interest rates. For example, you borrow from a bank at 12%. These quoted rates are usually annual percentage rates or APR rates. However, in a short while, you'll observe that these are not effective rates. Your bank tells you that you have to pay 1% monthly installments. Now your effective rate becomes 1.01 raised to the power 12 minus 1, which is 12.6825%. While this mere increase of 0.6825% may seem like pocket money, when you associate it with thousands of crores and millions, it will be a huge sum. As a general rule for payment or compounding frequency of m times per year with a quoted annual percentage rate of r%, the following formula can be used to compute the effective interest rate, that is 1 plus r upon 100 into m raised to the power m minus 1. Here r is in percentage. As the period of compounding frequency becomes smaller, the effective interest becomes larger. For a special case, when m becomes infinitely large, then this value converges to e to the power r upon 100. For a period of t years, the effective amount will be e to the power rt upon 100, and effective interest rate will be e to the power rt upon 100 minus 1. This is called continuous compounding. In financial market research, predominantly continuous compounding is employed in the computation of returns. For example, if the opening price P0 equal to 15 rupees and closing price P1 equal to 20 rupees, then returns as per the continuous compounding will be computed as natural log of P1 upon P0. Let's consider this example of compounding interest. If your compounding frequency is 1 year and 12% annual percentage rate APR, then your effective interest rate is 1.12, which is 1 into 1.12. Now, if you increase the compounding frequency and compound it 2 times a year, that means interest is paid every 6 months, then it is semi-annual compounding and 2 times compounding will happen. If interest is paid every 4 months, then over the period of 1 year, the compounding will take place 3 times. So compounding frequency increases to 3 times. Similarly, as we keep on increasing, let's say we take interest payment intervals as 1 month, then compounding frequency is 12 times. And as we keep on increasing, a very small period that is less than 1 day is often referred to as continuous compounding because money is being continuously compounded or interest is paid as extremely small intervals. And therefore, we can see that as the period of interest increases, compounding decreases. As the period of interest decreases, compounding frequency increases. Let's conclude this with a simple example. First, if the compounding frequency is 1 times, that means period is 1 year, then effective interest rate is 1.12 minus 1, which is 12%. So there's no excess over 12%. However, if the interest paid at interval of 6 months and compounding frequency is 2 times, then your effective interest rate is 1.06 raised to the power 2 minus 1 equal to 12.36%. So the excess over 12% is 0.36%. As we keep on doing this, let's say we compound it each day 365 times a day, then your effective interest rate is 1 plus 0.12 upon 365 raised to the power 365 minus 1, which is 12.7475%. And an excess interest rate over 12% of 0.7475%. For extremely small period with continuous compounding, you have e to the power 0.12, which is 12.75%, and an excess rate of 0.2575%. So this is the maximum frequency. That means interest is paid almost at as small as interval as t to the tending to 0. So as the compounding frequency increases, the excess interest rate over 12% also increases. To summarize, the effective interest rates are a function of compounding frequency. As the compounding frequency increases, interest is paid more frequently and therefore the effective interest rates also increase. The maximum frequency available or that can be generated is called continuous compounding. To summarize this lesson, financial markets provide a very important conduit for individuals to optimize the time pattern of their consumption. The demand and supply of funds determine the efficient clearing prices and therefore the interest rate environment that prevails in the economy. Expectations of interest rate from security are determined based on the risk of the security. Risk of a security represents the increased uncertainty in outcomes. The wider the possible outcomes, the more the risk. For a given level of risk, investors prefer instruments with higher expected returns, and for a given level of expected returns, investors prefer instruments with lower risk. We discussed the computation of standard deviation and variance, the two most important measures of risk in finance. We also discussed the properties of normal distribution, which is most often employed in modeling the financial market returns. Lastly, we also discussed the concept of interest rate compounding.